Welcome to the Transformer Lab channel. We will explore the architecture, the math, and the inner workings of the LLM models. Transformers revolutionized AI by changing the fundamental way computers process language. Older models, like RNNs, were forced to read words one by one. This serial process was slow, and the model often forgot the beginning by the time it reached the end. Transformers changed the game. They read the entire sentence at once. This allows them to instantly understand relationships between words, regardless of distance. First, we break raw text into small pieces called tokens. Each token is converted into a list of numbers called an embedding. But the model doesn't inherently know word order. We fix this by injecting positional encodings. These act like timestamps, ensuring cat-sat isn't sat-cat. Self-attention lets every word look at every other word. To do this, every word gets 3 vectors: query, key, and value. Think of a file search. The query is what you are looking for. The model compares the query to every key using a dot product. This creates a score. A high score means the words are strongly related. We squash these using softmax to get percentages. Finally, we multiply these percentages by the values to create a weighted summary. Irrelevant words are ignored. This result is the new context vector. Doing this once isn't enough to capture complex language. So we use multi-head attention to run this process several times at once. Each head looks at the sentence from a different perspective. One head might focus on grammar, another on meaning. The results from all heads are stitched back together. After attention, the information moves to a feed-forward network. This layer expands the data's dimensionality, processes it with non-linearity, and compresses it back. But deep networks forget things, so we add a residual connection. This creates a highway for information to flow unchanged, solving the vanishing gradient problem. Finally, we apply layer normalization to stabilize the learning. It forces the numbers into a consistent range, preventing chaos. The original transformer was designed for translation, consisting of 2 distinct halves. The encoder on the left processes the entire input sequence at once. It uses bidirectional attention. Every word can see every other word. This creates a rich context vector that captures the deep meaning of the sentence. The decoder on the right is different. It generates text one step at a time. It uses masked attention. Words can only look back at previous words, never forward. But here is the magic: cross-attention. The decoder uses the encoder's context map to query information while generating. Today, we often split them. We use the encoder for understanding tasks like BERT, and we use the decoder for generative tasks like GPT. The decoder gives us one final vector representing the meaning of the next word. But computers don't speak meaning, they speak numbers. The linear layer projects this vector onto the entire vocabulary, 50,000 plus words. These are logits, raw, unnormalized scores. Some are negative, some are huge. We pass them through a softmax function to turn them into probabilities. The model sees that Matt has the highest probability, 65%. So it outputs Matt, but the job isn't done. This word is fed back into the input to generate the next word. This is called autoregression. the output becomes the new input.